We're moving into the last section before exam 3, and this section is introducing us to something completely different and something very abstract. But it works, and it's the top of it's the most current knowledge that we have involving the electrons. And what's kind of curious to me is if you're talking about electrons, they do energetically impossible things, and there's some things you can't even measure with them. But what's kind of odd is if you're talking about gravity, you have to pull out Einstein's laws of relativity and things. If you're going to talk about baseballs, and big objects, macroscopic objects, automobiles and people, you got to talk about Newton's laws. If you want to talk about what's going on at the electron level, you have to talk about quantum mechanics. So there's all these different books you're essentially pulling off the wall, right, for different problems. It doesn't seem right, right? And there should be one book, and everything agrees, right? One set, one grand unified theory is the golden gate, what all these physicists are after. And right now they have several possibilities, but one for the grand unified theory is string theory. But they haven't figured out a way how to test it. So it's kind of odd for that to be a science, but it is. So quantum mechanics, though, for the chemistry of the very small, the size of the electrons, has yet to be proven wrong. And it's really, really useful, and it's really powerful. For example, if it can only explain, here's magnesium. It's just two forms. One is in a strip, the other one is just powdered. But the optical properties are tremendously different. One's black, the other one's shiny. The only way to explain that is the chemistry of the really small, quantum mechanics. If we have, to try to get into this a little more, if you take a look, what I gave you is a spectroscope. And you're going to hold it this way. You're going to look through this part. But what's key is you see the little slit on the end. You want to line that up with like the fluorescent light. So you look through there. You got to grab one. You look through there, line that up with the fluorescent light, and what do you see in there? The whole light spectrum. What's the name of the guy that gives you every color in the light spectrum that we can see? Roy G. Bibb. Red, orange, yellow, green, blue, indigo, violet. They're all there. And it's just this big smear, right? Okay. So light is actually, well, when it wants to. We're already getting into quantum mechanics. Light can behave like a wave when it wants to. It can behave like a particle in other instances. So here it's actually kind of behaving like, if you think of a wave, like at the lake, you've got the peak and then you've got the trough part. You take that physical distance, it's actual physical distance, because light is acting like a wave. You take that physical distance for the color red. It's going to be different than the physical distance for blue. Blue's actually going to be a little bit shorter, right? Red's going to be the longest. They have all these different distances. Well, if you can take a physical object that has that periodicity to it, that kind of step, that's going to be really tiny. What do you call it? Those oyster shells. They have a lot of that calcium deposits. And if you look at the microscopic level, they're almost like steps. And the steps aren't uniform, but in a certain area of that shell, they're uniform. They might exactly match red, so it reflects red. Another area exactly matches green, so it looks green. So those oyster shells, right, some kind of opalescent kind of thing is what you see, like pearls. And however, with what you're looking through the end of this is a grating, and those plastic lines that you can't see, they exactly match those colors. They allow it to diffract and bend it. So what you're actually seeing is the individual packets of light, like the red packets, the blue packets, the red packet. Like with Alejandro's shirt, you're seeing the red. But why aren't you seeing the other colors? His shirt is absorbing all the other colors. How are they absorbing? The only way to explain it is quantum mechanics. So how did all this start? Well, this is the part that I just don't, I can't relate to how people do this. Right? In early 1900s or there back in that time frame, they're playing around with electricity. Edison had his light bulb, and they're isolating all the pure elements on the periodic table, and they're getting them, and they're killing like poor Madame Curie and things because it's radioactive. And, they didn't know, but they're isolating all these elements. So they isolated some elements, like gases. Someone puts it in a tube, and then someone puts electricity across it, right? Now, what possesses people to do this? It's a genius. It's the guy that we would be teasing as freaks in school, probably, right? But they're the geniuses, so they discovered this. And then, well, they didn't have your nice grating that you have. They had the prisms, really dark room. They looked through it. Now, to see what they saw, you have to actually line up that slit with that lamp, okay? Line up that slit with the lamp. I think we have too much sunlight. You can't, you're seeing the sunlight. Shoot, I'm going to have to put it somewhere else. Let's try putting it over here. Get it away from the sunlight. There, it's much better here. So that slit has to perfectly line up with the lamp. You got to hold it the other way, Alejandro. Right? If you line up that slit perfectly with that lamp, you're going to see, I see a purple line off to the side. I see a purple line, a couple greens, this bright orange, then some reds. But you have to line up your slit perfectly with the lamp, and you'll see it. Can you get it? Do you see it, Jonathan? Right? Do you see those lines? Right? I see a purple, a couple greens, bright yellow, orangish thing, some reds. Okay. Then they took a different one. Different gas, right? Because they isolated these elements. That was helium. There's mercury. The only liquid metal at room temperature. Line up this one. You see lines again. They're just separated differently, and they have different colors. Right? So they can, each element exhibits its own fingerprint of colors. So they can use this, I mean, it's going to be a lot more expensive, but build some fancy things, they can figure out what's in the stars. Right? All the elements in the stars, just by seeing all the lines. Okay? So what this led to gotta move this out of the way. What this led to was a guy by the name of Bohr. Now his theory is way off, but it gets across something that's key to quantum mechanics. So that's why we still talk about it today. If by this time, in Bohr's time, they already had the idea of the hard core nucleus, which has what charge? Positive, right? And they already had the idea through like the gold foil experiments that, man, these atoms, they're all empty space, except for this really hard core. So Bohr says, okay, X is my nucleus, and it has this nice positive charge, hard core, and then I've got these possible orbits that an electron can be in. Because at that time, they knew mostly empty space, electrons are negative, and then he says, okay, well, that electron, if it's farther out, man, I bet you it's got more energy. Because it's negative, the nucleus is positive, and it's farther out, spinning around in that one orbit. It has to be in that orbit, going in that circle. It could jump from that orbit to this one, right? Maybe number these guys or something, right? And if it jumped from orbit 1 to orbit 2, let's say it gave off red light, right? And then it could jump, hey, how about instead of jumping from 1 to 2, let's jump from 1 to 3. And then let's give off green light. Higher energy, right? The highest energy this guy can jump is from the outer to the very inner, and that gave me a blue line. Right? I could jump from here all the way to the inside, and maybe that would be a blue light, a blue line. Okay? Because it's only that light. It's only that single color of blue. So it had to be that orbit going to that orbit. And all these different elements are going to have different orbits. Okay? But if you want to explain how an MRI works, if you want to explain how, if you've seen those pictures of like bed bugs and things that are always gray, those electron microscope pictures. If you want to talk about how an X-ray machine works, or this model doesn't work. It just bombs. You can't use it. But the idea of it giving you these electrons having only certain possible energies is key, is fantastic. But what's wrong with this? What they found is, again, you got to do the math to find this out. That math would say, okay, this baseball is giving me a sunburn. If nature behaved this way, as Bohr's model, this baseball would be giving me a sunburn. It's not giving me a sunburn. And does it even emit light? It does. If you have to be a firebug to really kind of have an inkling for this. You have the campfire, but no flames. You dig in those coals. Weren't they kind of like deep red? Okay. It doesn't have to be wood. It could have been a baseball. It could have been Alejandro's foot. It doesn't matter. You heat it up to the temperature of that coal, it's going to glow dark red. You get it hotter. What's the next color? Orange, right? The hotter you get, the higher energy it emits. So it's going to start glowing orange. You get something hot enough, it's going to go yellow, green, blue, indigo, violet. Then you're not going to see it anymore. It's going to be ultraviolet and give you a sunburn. Really, really hot. But any object will do that. So Bohr's model, it's on the right track. It just doesn't work, right? Because it's not, baseballs don't give you sunburns. So what does work? Quantum mechanics. So what they did is they said that, okay, the key ideas here are that these electrons, anything is possible, but only certain things. Does that make sense? Not really anything is possible. Say a lot of things are possible, not infinite, not everything. A lot of things are possible, and they each have their own probability, but not anything is possible. Does that make sense? It's kind of like, I can either go to Walmart, H-E-B, or Fiesta, and I've got a 50% chance of going to this one, 80% chance, and I can't go to any little other place. That's it, just those three. Or I'm going to throw this baseball across the room and hit Dulce in the head. Okay? Now, we have no idea, and this is, if it was the size of an electron, we would have no idea how this baseball left my hand and hit her head. We have no idea how it got there. We just know that it left and it arrived. Those are the laws that you got to put up with for quantum mechanics. Funky, weird, energetically impossible things. Okay, if you wanted to make some guesses on how this electron-sized baseball hit Dulce's head, you'd have to take all these possible paths. There's not an infinite number of them. There's some possible paths, and some of them are energetically impossible. It's going to have to pass through the roof, come back down, and hit her in the head. In fact, that's what had to happen for that MRI to work. Energetically impossible things had to be going on. Energetically impossible things for those electrons they had to be doing to get those little electron micrographs of what a bed bug looks like, electron microscope pictures. And it's just something you have to get used to. But I kind of find comfort in it because I was a defeatist. I was saying, hey, shit, this is gonna, you have no chance, you have no choice. This is what happens. But now, no. Shit happens, right? You have no control. There's certain likelihoods, but at the very molecular level, electron level, anything's possible, right? You have all these possibilities. There's some are just more likely than others. So determinism is totally out the door. Free will is totally what quantum mechanics is about. Okay? But anyway, that's neither here nor there. But Okay, so they had some big name guys in here. They had some Schrödinger equation. You can start getting into all the terminology, but the point is they figured out the exact electron levels, what's going on for the electrons for one element. To this day, this is all we can figure out is this one element. What do you think it is? Hydrogen. Why? Because it has how many electrons? That's all we can handle. With all of our computing power that we have now, hydrogen's it. So, where's my pen? Hydrogen is it. So you should be asking, Daisy, why the hell are we studying quantum mechanics? Life is a lot more complicated than hydrogen, right? We got really good at making approximations with quantum mechanics. So good that you find a problem, leukemia, cancer, whatever. If there's, for example, let's focus down on cancer. There's some defect in the DNA, and you kind of know what that issue is, because all these people have this particular cancer. So you identify it with little microscopes and stuff. You see what this looks like. So you get the chemical model for it. And then you use quantum mechanics to design drugs that how it's going to fit, how it's going to interact, what is going to be the effect of this drug on that anti-tumor drug. So, and it takes a lot of big computing power, but it's really powerful. Imagine, that's just the chemist sitting there at the table working on the computers, right? This model, this anti-tumor drug, he's possible, man. He could intercalate in there and interact with this blah, blah, like all the little steps. This could really work. What do? They go send that off to the lab, they test it, and then they make buku dollars. So it's really powerful stuff. And or what not to test. Think of it that way. Do not test this class of drugs, this class of compounds, because that is not going to help with this cancer problem. Only do this type. Inject this stuff in the rats, not this stuff. And it's really powerful. So anyway, we got really good at guessing, even though hydrogen is the only one we can solve for. Truly, perfectly. Okay, so they solved for the hydrogen. They call it the Schrödinger equation, and they found some solutions. In other words, all the energies of the electrons. And that doesn't mean that you know everything. That just means that you know the probability of these different things happening. So that doesn't mean you can control stuff. You just have a better handle as what's going on. But these solutions are referred to as atomic orbitals, or hydrogenic orbitals, because it's the hydrogen atom, and are pictured below. So, and if you take more, this is where these are called the electron clouds, or whatever you'd like. 99.9% of the time, this is where the electron's supposed to be, at these particular energies. So, if you give this electron more and more energy, you get more and more shape. It's kind of the same thing if Daisy's holding a slinky, I'm holding the other slinky, and somehow we get in sync, bringing it up and down, you're going to have all this vibrating here and then nothing here, vibrating here, nothing here. And if we do it even harder, we'll get more of those little guys. If we go slow, they'll just flop up down the middle, right? But if you take a closer look at this, and you can't really see it very well, but right here, like these two they look the same, don't they? But they're not. Right here is one of those parts of the slinky that's not moving. In other words, we're doing that slinky thing, and it's vibrating really hard, and then it's not moving. Vibrating really hard, not moving. We call it a standing wave. And it's hard to do. I'd bring it in, but it's really hard to get going. But you can do it. But what I'm trying to say is right there is one of the parts where the slinky's not moving. They call those nodes. And the darker the region, that's where the electron's supposed to be more likely to be. But that's a node. It's totally empty space there. So you've got this possibility of the electron being out in this kind of thick kind of shell area. And then you've got this area where there's absolutely white. There's no way the electron will ever be there. And then you've got the electron in the middle. Well, this is the hydrogen atom. How the heck did hydrogen's electron jump from, if it ever is in the middle, out to the outside? It can never be in between. It can't go from there to there. So right off the bat, solving hydrogen, it's doing impossible, energetically, or just simply impossible things. So we just have to get used to it. with quantum mechanics. It's like I said, there's not a problem this has come across that it can't solve at the electron level. So it's just how life is. It's how nature is. Okay? And like I said, with the MRI, it's doing energetically impossible things. But when boiled down, these solutions to the hydrogen atom are described using quantum numbers that follow the rules as organized in the below table. So one more time, the reason why we talked about Bohr is he got across the idea of these energy levels, right? Quantized energy levels. Energy is quantized at that extremely small level. And he brought that idea across pretty dang well. So that's why we stick with introducing him still. And how do you describe these quantized energy levels? If all these electrons, well, what energy do these electrons have? How many of them are in this energy? How many of that? Do any of them have the same energy? Well, all these rules tell you. And it's just statistics is the background of it, and we just kind of got to learn the rules is all we're going to learn. We're not going to go into how they got these rules, but we just need to get used to the terminology and know the table, and we'll be set. So the quantum number description, we have let's see, I don't want to lose track here. Oh, yeah, shell, not principal. Shell, okay. They call this first quantum number is a principal quantum number. So what they're going to get when all this is said and done, each electron in an atom, like, for example, carbon has, 6 electrons. Each electron is going to have its own set of quantum numbers. So it says it describes its energy, the orbital that it's in. The orbital, remember, that's going to be one of these guys, pretty much, and where it's likely at. So, and some of these are farther out than others, and you can get into the reactivity and what that electron is doing, where it's at, all the chemical properties of it. So what we're doing with this box is describing all these quantum numbers that we're going to use to assign to each electron. So the first quantum number we're going to talk about is the shell. They call it the principal quantum number with little number n. It really describes the energy. This guy really describes the energy of that electron. Okay, so he's the main energy level. And then but with that main energy level is associated some other little energies, so they call it the subshell. So each shell has its own associated subshells. And they call that the angular momentum quantum number is the next quantum number. Angular momentum quantum number with a little cursive L. Okay. And angular momentum is something that you're not used to seeing. You've seen, I don't know, throwing a baseball at Oscar, right? The baseball has momentum. So he just has to apply some momentum this way to stop it, right? That's linear momentum for objects. Angular momentum is why you can ride a bike. So again, it's the same idea as it's momentum. This baseball had momentum. That means it wants to keep going same direction, same speed all the time. A bike wheel has momentum. It wants to be going at the same speed, same direction. What's its direction, though? It's angular. So it's spinning about this axis. It doesn't want to change that axis. It wants to keep it there. That's angular momentum. And since it wants to keep it on that axis, it's going to be really hard to twist it. So you just have to trust me that it's hard to twist this guy. That's torque. It's hard to apply a torque, that's a twisting force. So that's angular momentum. And there's got to be a lot of angular momentum here, because look at these guys. They're coming back on themselves. You have to stay in that orbital 99.9% of the time. The subshell. And the next quantum number is the description would be the number of orbitals in a subshell. So once you know what the subshell is, you can just figure out the number of orbitals using the magnetic quantum number, it's called. And it has a little symbol, m sub L. And the last one takes into account line splitting. So if you were looking at one of these lamps through that spectroscope again, and then someone put a big magnet between you and the lamp, all of a sudden you don't see just that one red line anymore. You see two red lines. All the lines end up being split. So this accounted for that, the spin quantum number. Okay, so we need to know the names, and pretty much if you know what the shell is, these possible values are going to take the rest of this into account. If you know what the shell is, then then only certain L values are allowed. If only certain L values are allowed, only certain M sub L values are allowed, and it just goes on down from there. And that's how the energy gets quantized. Only certain possible values are allowed. And where does it start? For example, N could be 1, 2, 3, just positive whole numbers. Okay? And I wish they would stop there, but they also say, instead of saying N equals 1, they'll say, oh, you're in the K shell. You're in the capital L shell. So you have to know not only the numbers, but the letters that get associated with it for the principal quantum number. K, L, M. Okay, now oh, it all is alphabetical. K, L, M, N, O, P. Why they start with K, I don't know. Right? And then the angular momentum quantum number, it goes from L equals 0 up to N minus 1. So it all starts with knowing that N quantum number, and then you can figure out what your L could be. So how many subshells are there if you have any particular shell? Well, you just pick an N. Let's say N is, let's go off to the side. Let's say N is 3. Well, then L will go from 0 up to N minus 1, which would be 2. So that means L could be 0, 1, or 2. So the terminology there would be that, hey, for N equals 3, I actually have 1, 2, 3 subshells. Okay. And so that means L could be all these 0, 1, 2, 3, 4, 5, on up. And they want you to know, just like with the shell, they want you to know little letter designations. So an L equals 0 subshell, they're going to call that an S, little s subshell. If L is 1, that's a little p subshell. L is 2, a D subshell. S, P, D, F, and it just goes alphabetical after that. Okay, so they want us to know both. The number of orbitals in a subshell. So I don't know. Now they're getting in even deeper. If you do have I don't know, the D subshell, or L equals 2 subshell, how many orbitals are there, right? M sub L goes from negative L to positive L. So, for example, if I had, I don't know, let's say L was 2, then M sub L will go from negative 2, and you just put in all the integers between negative 2 and positive 2. So that'd be negative 2, negative 1, 0, positive 1, positive 2. Right? So if little L is 2, that's the D subshell. I have actually 1, 2, 3, 4, 5 orbitals. And that's kind of what they're saying here. There's 5 types of D orbitals. Okay. And the last one, M sub S, can only be a positive a half or a negative a half. When we start drawing orbital diagrams, well, our little arrow will point up or it'll point down to take that one into account. Okay. So like I said, know this table, and then we can handle anything in the homework. Like here's the first question. How many subshells in the L shell? So subshells refers to which quantum number? Little l. So the question really is, how many different little l values do you have? Right? Because that'll tell you how many subshells you have. How many little l values do you have? Well, see, what I'm getting at is you're too fast. If little l, I have to know two things. Subshell, oh, that's little l. And then I also have to know, okay, that goes from 0 to n minus 1. Right? Those two things you got to know. And then L, so that meant little n is 2, right? So I have to go from 0 all the way up to 1. So I'm going to go from 0 all the way on up to positive 1. Are there any numbers in between the two? No. So I'm done. So the number of subshells would be 2. The answer would be 2. Okay. No, from capital L. Yeah, and I can't jump that high. It's right here. L corresponds to 2. So they can say n. They could have said n equals 2, but they're going to do this a lot. They're going to say the shell, instead of describing the shell with a number, they're going to describe the shell with their historical little letter there.
How do you know it's 2?
Because you have to memorize this.
Oh.
If K, capital K, that means n is 1. Capital L shell, n is 2. Capital M shell, L is 3, and on down.
It's always going to be like
It has to be like that. Yeah. Yeah, you have to know it, otherwise you're just out of luck. Try this one. How many subshells in the O shell? 0 on up to n minus 1. If I don't write it out, I'm going to screw it up. 0 on up to n minus 1. So that'd be from 0 to, well, I write 5 minus 1. So 0, 1, 2, 3, 4. Yeah, that's 5, sorry. Right? There's 5 different little L values. How about how many atomic orbitals in the P subshell? So if they're talking about how many atomic orbitals, we're supposed to be looking at what quantum number? The magnetic, that m sub L. He'll give you the number of orbitals for any subshell. So you have to figure out how many different m sub L's there are. That's m sub L. So I guess the two things you got to remember then is, okay, atomic orbitals, that's m sub L. And m sub L goes from, the other thing you got to remember, m sub L goes from negative L up to positive L. Okay, that's going to be negative 1 all the way to positive 1. So m sub L could be what then? Negative 1, 0, and 1. So that'd be 3. The answer would be 3. 3 orbitals. Okay. So for any P subshell, you have 3. Kind of look like that. Okay. Let's try this one. If the quantum number of an atomic orbital is 4, what are the possible values of L? N equals 4. L goes, Jonathan, from what to what? 0 on up to n minus 1, 0 all the way up to 3. Just type in all the numbers in between then. Pretty much just 1 and 2, right? How about if L is 3, what are the possible values of m sub L? See if you can answer that one. Yeah, go from negative L to positive L. List them all out. Just list them all out. Let's jump down to 4, because 3 is kind of redundant. So they want you to give them the notation. And how does this notation work? You always give the n number, and then you give the p, I guess you could write n number, I guess, the n number, and then you write the p letter, not the p, L, right, or angular momentum quantum number letter. So, for example, like 3s would be n is 3, L is 0. Okay? So what letter designation would you give for A then? It have to be 3 what? Danielle, what would it have to be? 3, L has to be 2. 3, she says 3D. I got to write it out, otherwise I always screw up. Let's see. It goes S, P, D, F, G, H, and on. So 0, 1, yeah, she's right. Right, because L is 2. That corresponds to D. See how I did that? I just had to list them out. Life is easier that way. What would B be? 4S. Good. Let's jump down to these, this EX5. So what they're heading us up for and preparing us for is each electron is going to have its own set of quantum numbers. So it would be a good idea to be able to recognize quantum numbers that you just screwed up on, right? So I think there's 3 in here that are just impossible. You can't have these. They're not following the rules in the table. Can you find one of them? I hear C. What's wrong with C? You're right. What's wrong with C? N can't be 0. That one's impossible. I think there's 2 more that are impossible. N can be 2. L goes from 0 to n minus 1, so that's okay. So A is actually okay. What's wrong with B? Yeah, that's right. This guy, right? L has to be 0. L has to be 0. Because n's only 1, and L goes from 0 to n minus 1. So I think there's one more that's messed up in here. E. What's wrong with E? M sub L can only go from negative L to positive L. So it can't be negative 2. Right. So if you know that table, you can do anything in the homework. This one's actually okay. So have a good weekend.